Hello, and today's video is going to be about implicit differentiation. So, if you don't know what implicit differentiation is, it's basically when you don't define y in terms of x explicitly. So when you have, for example, x plus y equals 2, you don't rearrange y2 equals 2 negative x and solve like that. No, you just differentiate this. And why people do this is because in some cases, this is faster. Probably not in this case, but as we will see, it's a pretty useful tool to have. And what you will have is that in your dy dx, you will end up having y as a variable. So the strategy that I would say you use for this, now it's a bit abstract when I just mention it like this, but you will see it in an example. So first, you take the derivative of x on both sides, obviously, of the equation. Then, where there is a y, you take the derivative of whatever expression you have of y and you times dy dx. And basically, if you think about it, these two cancel out, and then you go into just whatever your y expression is, dx. So you kind of rewrite it so it can be simplified. And then lastly, you just rearrange the equation and get the dy dx. So how about we look at an example? Alright, so our first example will be pretty basic, where y squared plus x squared equals 1. Oh wow, familiar, a circle. Ooh. Anyway, so in order to start this, we will take the derivative of x from both sides. And we simplify this, so dx dy plus dx of x squared equals 0 because that's a constant. And I'm just going to leave this for a bit later. And here you can just solve it plus 2x, right, using the power rule. And then you're left with ddx of y squared. Now, this doesn't seem like it's gonna work, so we have to do something with it, and basically what we do is that we say dy squared over dy times dy over dx plus whatever expression you have left over. And then what you do is you solve, so it's 2y, and you keep the dy dx plus 2x equals 0. And I think you can see where we're going with this, because now all you have to do is you have 2y dy dx equals negative 2x, and then dy dx is going to equal negative 2x over 2y. And this is our final answer right here. So if you look back at the process, you can see what I mean by first, we take the derivative in terms of x of both sides. Then, whenever we have a y, we rearrange it to look somewhat similar to this. So here our only y was here, and then we rearranged it so it would look like this. And then lastly, we just simply rearrange the whole equation in order to get our dy dx on one side. Oh, and just to mention, I forgot, this simplifies to negative x over y, by the way. Don't know how I forgot to do that, but yeah. This was a pretty simple example because we only have one y, but in the next one, we can look at when there are multiple y's and when there are y's together with x's. Alright, so this is our second example. And to start off, we'll take the derivative of both sides. And the first term over here, that is pretty simple because you just have 6x squared. Now here, I'm just going to leave this for now, because we're going to deal with this later. Minus 0, because for the constant, is equal to 0. So what do you think we could possibly do with this situation that we have going on over here, where we have both an x and a y together as a term? I mean, if you think about it, you could do, for this part of the equation, the power rule. So when we rewrite this, we have 6x squared plus 2xy, because the power rule is the derivative of the first variable, times the second variable plus the derivative of the second variable times the first variable, plus x squared times dy dx. And then we have this left over, which we saw in our last example. So we have d of y squared dy times dy dx. And all of this is going to equal to 0. Makes sense? And now, well, we can just factor out our dy dx, because our final goal is to have dy dx on one side. Alright, so now we just continue going and rearrange. So we have 6x squared plus 2xy plus dy dx of x squared plus 2y, because the derivative of y squared is 2y, just because I kind of skipped that step over. I'm just explaining it right now. And then we can move that other thing to the side, so we have dy dx of x squared plus 2y is equals to negative 6x squared negative 2xy, and then our final step is just dividing by what we factored. Equals negative 6x squared minus 2xy over x squared plus 2y. And this is our general formula that we have over here. And all we did is we just, once again, applied that little strategy that I wrote in the beginning, where we take the derivative of x, and then in this case, we had to use the power rule over here, and then we got our general equation. Now, we have to find this at the point negative 1, 2, and to do this, we just plug in negative 1 for x and 2 for y. So negative 6 plus 4 over 1 plus 4, we get negative 2 over 5. And that is our final answer. Alright, so I hope these two examples made it more clear to you for how to do implicit differentiation, and you can apply this anywhere. Like, you don't need to just stick to the power rule, obviously, and don't be afraid if you see something you're like, I don't know what to do with this. Like, see if there's any other derivative rules that you know that you can use in order to solve this, and then just write it out in a form similar to this, or sometimes you don't even really need to do it, like over here, where our y is just y. So this got us the form needed correctly. We didn't even have to do anything more. For example, if this was y squared, I'm just going to do this in green. If this was y squared, then here it would be dy y squared, and then we would have to do something like this again. It would be x squared 2y, and then we would have to factor that out as well. But I hope you enjoyed this video, and I hope you refer back to this little strategy. And thank you for watching.